Today we're diving into deep planning, benchmarking long horizon agentic planning with verifiable constraints by the Quen team at Alibaba Group.
Yep.
So for the 1-minute summary, we all know LLMs are great at short tasks. This paper, though, it just exposes this massive failure when it comes to long horizon planning.
Things like planning a multi-day trip or a complex shopping list with a really strict budget.
Exactly. So the authors built deep planning, a new benchmark that uses these isolated sandboxes and, crucially, code-based verification. No LLM grading another LLM's homework.
And the results are humbling, to say the least.
Even frontier models, and they list some unreleased ones like GPT-5 High and Claude 4.5 Opus, they struggle with what's called case accuracy.
Meaning they get the individual steps right, but the final plan as a whole, it's often completely broken.
Right. And the big takeaway is that reasoning models, the ones that think before they act, they do way better, but even they are failing to solve most of these planning tasks.
And that distinction you made between getting a step right and getting the plan right, that is the entire ball game here.
It is, isn't it?
Yeah, we're seeing models that can write, perfect Python code to query an API, but then they just completely fail to realize that the flight they just booked lands 2 hours after the hotel check-in desk closes.
So let's back up a bit. I feel like every week there's a new agent benchmark paper. We have Toolbench, Travel Planner. Why did the Quen team need to build another one? What was missing?
It's a fair question. The issue with a lot of the existing benchmarks is that they mostly test what the paper calls local step-level reasoning.
Okay, what does that mean in practice?
So imagine you ask an agent, find me a flight to Paris for under $600. That is a local retrieval task. The LLM hits an API, filters a list, and gives you an option. It's pretty straightforward.
Right, it's basically just a fancy search engine at that point.
But deep planning is all about global constrained optimization. And this is where you have this whole web of dependencies.
So you're not just finding a flight.
No. You're finding a flight that fits a budget, but the price of that flight then changes how much you have left for the hotel. And the hotel's location dictates your taxi costs. And the flight's arrival time determines if you can even make your dinner reservation.
It's a house of cards.
That is the perfect analogy. In older benchmarks, if you got the flight right, you got a point. Simple.
Yeah.
In deep planning, if you get the flight right, but it makes you go $10 over budget on the hotel 3 steps later, the entire plan is a zero.
Oh, zero. Wow. It's totally binary.
Completely. And that sounds frustrating for the model, but for anyone trying to actually deploy this stuff.
It's way more realistic. If I build a travel agent app and it books a flight that makes me miss a meeting, I don't care that it's successfully called the flight API. The product failed me.
And that's why they identify these 3 core competencies. First is proactive information acquisition. The agent has to go looking for hidden info. It can't just guess.
Which, knowing LLMs, they love to do. They'd much rather hallucinate a variable than actually look it up.
Then you have local constrained reasoning, filtering options. But the third one, global constrained optimization. That's where the carnage happens.
That's the house of cards.
That's making sure the combination of all your choices actually works together. And the paper shows that current models are just fundamentally bad at it.
So before we get to the results, and I'm excited for those, let's look under the hood. How do you even build this? It's not just a text file, right?
No, you can't use static text. You need a simulator. So they built this offline sandbox environment with actual databases and Python APIs.
So it's like a fake internet.
Essentially, yeah.
Yeah.
It guarantees reproducibility, which is key. And they split the tasks into 2 big domains, travel planning and shopping planning.
Okay, let's start with shopping. I feel like that sounds easy. Buy milk, buy eggs. How hard can that be?
You would think so, but they turned it into this combinatorial optimization nightmare.
Oh, wow.
There are 120 tasks, 15 different APIs.
Yeah.
You have to search products, get details, check stop. But the real twist is the coupon system. Yeah, they implemented this really realistic coupon logic. So you have same brand coupons, cross-store coupons. The challenge isn't just buying the items, it's figuring out which combination of items from which sellers gets you the absolute lowest total price.
Okay, give me a concrete example. How does an AI mess this up?
All right, so imagine your cart has $290 worth of electronics, and the system offers a coupon. Spend $300, get $50 off.
Right. A human sees that and thinks, okay, I'll add a $10 cable to trigger the discount. Your total cost drops from $290 to $250.
Exactly. You spend more to save more. But to an LLM, buying that $10 cable at that specific moment looks like a violation of the constraint to minimize cost.
Ah, I see. It sees it as an extra expense.
It fails to look 2 steps ahead to see that the local expense triggers a massive global deduction. It's penny-wise, pound-foolish on a purely mathematical level.
That is fascinating. It's getting stuck in a local minimum because it can't see the whole landscape.
And then you have travel planning. 120 tasks, 9 APIs. This is less about pure math and more about temporal rigidity, down to the minute scheduling.
This is where that House of Cards thing really kicks in.
It does. They use what they call a layered task generation system to make these really hard. So they'll start with a simple skeleton, trip to Beijing.
Okay.
Then they add personalized constraints. I want to eat at a star-rated restaurant. But then comes the gotcha layer,
Yeah.
the environment constraints.
Like what? What's an example?
Like the user wants to visit the Forbidden City on Tuesday, but the database has a hard-coded rule. It's closed on Tuesdays.
Oh, no.
Or there are only 2 flight tickets available for a party of 4.
And the agent has to figure that out itself?
It has to call query attraction details or query flight seat. If it just assumes availability, which they so often do, it fails the task.
I want to touch on the grading. You said it's not LLM-based, so we're not asking GPT-4 to grade GPT-5's homework.
Thankfully, no. This is one of the strongest parts of the paper. It's all code-based evaluation.
Yeah.
For travel, they have a common sense score. They literally run scripts to check things like, is the route physically possible? Can you get from the airport to the hotel in the time allotted? Did you try to be in 2 places at once?
So it's basically a unit test for the entire itinerary.
Exactly. Then there's a personalized score for user requests. But the metric that really matters, the one that just destroys these models, is case accuracy.
Okay, define that for us.
Case accuracy is. It's the strict standard. For travel, you have to pass every single common sense check and meet every user need. For shopping, your final cart has to match the ground truth optimal solution perfectly.
So if you missed that coupon optimization we talked about,
0 points.
brutal. Okay, let's do it. Hit me with the leaderboard. Who survived this?
Well, this is where we get a little peek behind the curtain. The top model is listed as GPT 5.2 high.
Wait, hold on. GPT 5.2 high? That is not an API endpoint I can call.
No, it's not. The paper has a few of these designations, GPT 5 high, 5.1, 5.2. It implies the Quinn team had access to some significant internal or preview models from OpenAI.
Okay, so assuming GPT 5.2 high is the current king of the hill, did it crush the test?
It won, for sure, but crushed is way too strong a word. It got a case accuracy of about 44.6% on average.
Less than 50%.
And that's the best one. Right behind it was Claude 4.5 Opus with thinking enabled. But the real headline is the gap between the models that think and the ones that don't.
We're talking about chain of thought, internal monologues, that kind of thing.
The data is so stark. You look at Claude 4.5 Sonnet. Without thinking, it performs pretty poorly. You enable those internal reasoning traces, and its score jumps up significantly.
So for this kind of planning, that system 2 thinking isn't just nice to have?
It's a prerequisite, absolutely.
But even with it, 45% accuracy is, well, you can't ship that. You can't sell a travel agent that ruins your vacation more than half the time.
In the travel domain, it's even worse. The best models are barely breaking 35% case accuracy.
So 2/3 of the time, the agent is creating a plan that is physically impossible or just wrong.
Or it violates a core user constraint. Yeah. They might get a high common sense score, say 88% of the individual checks pass, but they always trip on one wire.
Like what?
Maybe the flight and hotel are perfect, but they schedule dinner at a restaurant that's a 2-hour drive from the hotel and only leave 30 minutes to get there.
So close and yet completely useless.
It just shows how fragile these systems are.
Okay, now, there was a really weird outlier in the data. Something about Google's model.
Ah, yes. The Gemini Anomaly. This is fascinating. They tested Gemini 3 Flash Preview.
Okay.
In travel planning, it really struggled. It had a hard time with all the temporal sequencing, the timeline stuff. But in shopping,
It did well.
it was the absolute king. It hit 60% case accuracy in shopping. It beat the entire GPT-5 series.
Whoa, that is a huge difference. Why would a model be a genius at shopping and, a dunce at travel?
It probably comes down to the shape of the reasoning required. Shopping is combinatorial. It's like a math puzzle, like Sudoku. You have to optimize a set of numbers all at once.
And travel is.
Travel is sequential. It's more like a crossword puzzle. Clue 1 leads to clue 2, which leads to clue 3.
So Gemini is a savant at Sudoku, but struggles with the narrative flow of a crossword.
It seems like it. It suggests that Gemini's architecture might be tuned differently, maybe prioritizing parallel constraint satisfaction over these long, sequential logic chains.
Let's talk cost, because I imagine getting GPT 5.2 to think through a 5-day trip is not cheap.
It is definitely not. There is a direct linear correlation between the number of tool calls and the performance. They call it the cost of intelligence.
How many are we talking?
GPT 5.2 High used roughly 224 tool invocations per task.
224 API calls for one plan.
I mean, think about it. Check the weather for 5 days. Check 3 different flights. Check 4 hotels. Check availability for each attraction. It adds up really fast.
And if you try to cut corners on the calls,
the model starts guessing, and that's exactly where the hallucinations creep in.
the paper also mentioned a difference in how the models make those calls. Something about sequential versus parallel.
This is a really critical engineering insight. GPT 5.1 High tends to use parallel execution. It bundles its calls together.
So it asks, get me info on these 5 hotels and 3 flights, all in one go.
Right. It's fast. It's efficient.
Well, yeah, it's
Sounds ideal, but
Yeah.
GPT 5.2 High takes a sequential approach. It checks the flight. It waits for the result. Then, based on that flight's arrival time, it checks the hotel. It takes 10 times more turns.
But it performs better.
Much better. Because it's reacting to the ground truth from the previous step. Parallel is great for speed, but if the first flight in your batch is sold out, all the hotel data you just requested is now useless noise. Sequential lets you course correct, in theory.
In theory, right, because they're obviously still failing. So let's get into the autopsy section. They analyzed 140 failed runs. What is killing these agents?
They found 3 main patterns. Pattern A is simple: information acquisition failure.
Just insufficient search.
Yeah. The agent just didn't look. It assumed a taxi from the airport takes 20 minutes without calling the route API. In reality, it takes an hour. The whole schedule breaks. It's basically laziness.
Or overconfidence.
Pattern B is implicit constraint violations. This is that party of 4 problem. The agent queries a flight, the API returns a flight object, and buried deep in the JSON it says seats available to.
And the agent just ignores that field.
Ignores it and tries to book it for 4 people. It's seeing what it wants to see.
And the third one?
The big boss. The most common error, over 70% of travel failures, is pattern C, global optimization failure.
Okay, give us the dramatic reenactment of a pattern C failure.
All right, real example from the data. The user wants to visit a specific museum and then have dinner at a specific restaurant. The agent books the museum for 3 to 5 p.m. It books dinner for 6 p.m.
Okay, an hour gap. Seems reasonable.
Except the museum is on the north side of the city and the restaurant is on the south side. The agent failed to check the travel time between those 2 specific points. It just assumed an hour is enough. With traffic, it's a 90-minute drive. The plan is physically impossible.
And to catch that, it would have had to proactively run that calculation between 2 intermediate steps, not just from the airport.
It requires a level of simulation, of running the tape, to see if the plan actually works, that these models just aren't doing yet. They're stringing together logical-sounding steps, but not checking if they cohere in reality.
So for all the ML engineers listening, the people actually building agents to refactor code or manage infrastructure, what's the big takeaway? If an agent can't plan a trip, can it really plan a database migration?
That is the scary part. The principles are identical. If you're building an agent, you need to be terrified of high match scores.
Because high accuracy on individual steps is deceptive.
Totally. Your agent might write the correct SQL query 99% of the time. But if it fails to check a dependency constraint, like a foreign key 3 steps earlier, the whole migration fails.
And a failed migration in production is a lot worse than a missed dinner reservation.
The paper basically says we have a desperate need for robust backtracking.
Explain that concept in this context.
When a human plans a trip and realizes the hotel is too expensive, we don't just give up, right? We backtrack. We go back 2 steps, pick a cheaper flight, and then try the hotel search again.
We can revert our changes.
We maintain a state of the plan. LLMs just plow forward. They hit a dead end like budget exceeded, and they either hallucinate a discount or just submit the broken plan and hope you don't notice.
So they can't say, wait, I messed up 3 turns ago, let me undo that.
Not really. It seems to be a fundamental limit of just being auto-regressive. Just predicting the next best token isn't the same as actually planning.
So we have reasoning models, but you're saying we don't really have planning models yet?
That's the perfect distinction to end on. We are simulating planning through chain of thought. We're generating text that looks like a plan.
But it's not the real thing.
True planning, where an agent maintains a world model, simulates outcomes, sees a problem in step 50, and can autonomously go back and fix step 2. That is still the next frontier. We are not there yet.
The paper is deep planning. If you are working on agents, I would highly recommend grabbing their code. Don't trust your own vibes-based eval. Run your model against this and see if it can book a vacation without leaving you stranded. It's a humbling reality check.